EC&M Asks is a video series that enlists the technical expertise of our brand's subject matter experts to answer our readers' most pressing electrical questions. Posted twice per month, these quick videos present Q&As on topics related to various installations, applications, and troubleshooting scenarios. When our readers ask, EC&M answers.
Hello and welcome to EC&M Asks. I'm Tom Sandri, Director of Workforce Development at Vector Power. I get a lot of questions about the practical use of partial discharge testing in a field environment. What we hope to accomplish today is for you to understand the difference between factory testing and the unique challenges we face when testing those same cables in the field. Now, PD measurements are utilized in various environments, including the field, laboratory, and factory for multiple purposes, such as qualification, quality assurance, and condition assessment. Understanding the fundamental differences among these environments is essential, as the metrics used and the strategies for noise mitigation can vary significantly. The main difference between field tests and factory tests lies in their application. Factory tests are conducted on unaged cables or accessories, while field tests are carried out on entire cable systems consisting of cables and accessories all installed together. Field tests involve systems with new and aged components, making them more challenging. Partial discharges are tiny electric sparks that can occur at defects in insulation, along interfaces, or surfaces between a conductor and a floating conductive component, not connected to the high voltage conductor or the ground, or between floating conductive components. When the intensity of the electric field is strong enough to ionize the medium surrounding these components, partial discharges will happen. These discharges do not completely bridge the insulation between the conductors. The defects may be located entirely within the insulation, along the interfaces between different insulating materials, or along the insulation surfaces, such as terminations or potheads. Let's really understand the physics behind partial discharge. Partial discharge occurs as a Townsend discharge within a small cavity. This process involves gas ionization, where a small number of free electrons, when accelerated by a sufficiently strong electric field, will lead to electrical conduction through the gas due to avalanche multiplication. When a PD event occurs, it generates an electromagnetic pulse that travels as waves through the shield cable system, which functions as a waveguide. Unfortunately, power cable systems are not perfect waveguides, leading to distortion of the pulses as they move away from their sources. This distortion is influenced by several types of cable system losses, which vary with frequency. The longer the cable system, the more significant the distortion becomes. Offline testing will require a source of test voltage. Voltage sources must be alternating current and can be characterized as power frequency operating at 50-60 Hertz. Now, this large and heavy equipment is typically reserved for laboratory and factory testing where transport is not a requirement. We also have near power frequency operating in the 30 to 300 Hertz band. The equipment typically consists of an excitation transformer connected in series or parallel with a variable inductance reactor. It is heavy and requires a dedicated truck or van to transport. Let's take a look now at very low frequency. The field industry as a whole really loves VLF testing. And the main advantage of testing at very low frequency is that it significantly reduces the size, weight, and cost of the required power supply, and thus offers greater attraction for field testing of medium voltage cables. It also makes the technology more available to a larger variety of clients. So, why is a VLF test set smaller than a power frequency test set? Well, if the test frequency were dropped to 0.1 Hertz, the capacitive reactance, as calculated earlier, becomes 1.6 megohms. Now, we further do the mathematics and we see that the power supply VA requirement has been significantly reduced. Thus, the main advantage of testing at very low frequency is that it significantly reduces the size, weight, and cost of the required power supply, and thus offers greater attraction for field testing of medium voltage cables. Now, we do have a relatively new player in the field, damped alternating current, also known as DAC. These voltage sources are lighter in weight and have lower power requirements than near power frequency excitation sources. The IEEE standard 400.4 addresses DAC voltage testing in the near power frequency range from 20 Hz to 500 Hz. Damped alternating voltages are generated by charging the cable system under test to a predetermined voltage level, then discharging the test object's capacitance through a suitable inductance. During the charging stage, the test object is subjected to a continuously increasing ramp voltage. During the discharging state, the test object experiences a damped oscillating wave, hence damped AC. How about we now talk about what are the resources that we can turn to better understand the complexities, process, and analysis of partial discharge. Among these, we have the IEEE standard 400.2 2024. This guide describes very low frequency, or VLF, withstand and other diagnostic tests and measurements performed using VLF energization in the field on shielded power cable systems. One of the best go-to documents is the IEEE standard 400.3, the new 2022 revision. This guide covers the diagnostic testing of new or service age installed shielded power cable systems, which include cable, joints, and terminations, using partial discharge detection measurement and location. Yet another standard we mentioned earlier is the IEEE standard 400.4 2015 revision. This one is for our new player, DAC. The guide outlines the practices and procedures for testing and diagnosing shielded power cable systems rated at 5 kV and above using damped alternating current. Hey, let's not forget about our international partners, the IEC 60270. This international standard applies to the measurement of partial discharge that occurs in electrical apparatus, components, or systems when tested with alternating voltages up to 400 Hz or with direct voltage. A wonderful research paper that I highly recommend everybody get a copy of, the Georgia Tech NETRAC Cable Diagnostic Initiative. And last but not least in our resource references, we have the ANSI NETA acceptance testing specifications and maintenance testing specifications. Now, speaking of NETA, if you like this content and really want to take a deep dive and go further, I'm going to be at the NETA Power Test 2025 conference in Orlando, Florida, providing a 4-hour seminar on this topic. Well, thank you for your attention, and that's a wrap on today's EC&M Asks.